Who was here for Dr. Apley's lecture on antimicrobials and resistance? That was a tough topic, wasn't it? That's a topic of right now. This is another tough topic. This is a topic of the future. So you dealt with the antimicrobial issue right now, as of January 1. This is going to look in the crystal ball a little bit and see how it might have been how PED virus got into our country and how other diseases could get into the country too. And I thought this only was a half an hour time period. So I created only a half an hour worth of slides. I think I only got 20-some slides, which is good for you because you get done quicker. You don't have to listen to me for an hour. And hopefully we have a lot of time to discuss. So if you want more detail about anything that I talk about, just fire away. If you disagree with me, go ahead and shoot me down. I like that kind of discussion. All right, so we'll make this real informal. And I want to thank the Minnesota Pork Board and Jill Resler for the invitation to come today. This will be a follow-up of what we talked about last year. So if you were here last year and kind of saw what we were inventing down in Pipestone and with South Dakota State University through the support of the Swine Health Information Center, all of the groups you see on the slide here, this will be a follow-up to that. So I think everybody probably knows who Pipestone is. Everybody knows who South Dakota State University is. Does everybody know who the Swine Health Information Center is? A marvelous initiative from National Pork Board, National Pork Producers Council, and the American Association of Swine Veterinarians to get funds together for really doing research to try to understand risk to our country, risk to our industry. And Dr. Paul Sundberg heads that up. And so I think everybody probably knows Paul. He's in his, I think, first or second year of leading the 5-year center program, and I can't give him enough credit. He's really, really done a great job. And so a lot of credit to what we call SHIC, or the Swine Health Information Center, but also to the group at South Dakota State University, Dr. Diego Dial, Dr. Eric Nelson, Dr. Jane Hennings, some marvelous virologists and diagnosticians at that facility. And then I want to credit our group at Pipestone for really thinking and developing these ideas and asking questions. How do viruses move around, say, not only from farm to farm, but how could they move into our country from some outside risk points? And our group does a lot of work in China. And so they get a chance to see foot and mouth, hog cholera, pseudorabies. And they've made some interesting observations on feed ingredients that are manufactured in China that come into the U.S. And you might remember some of the work we did in 2014 where we proved that PED virus could be spread to pigs through the ingestion of contaminated feed. Everybody remember that? Kind of old news now. Then we did some work on different ingredients, showing that some ingredients, like soybean meal, could harbor live PED virus for 180 days if you're out to cold weather. While others, like corn, the virus couldn't live in corn for even a day. So we started talking about there's some differences in how viruses live in feed ingredients. And then we went together and put together a model trying to simulate how contaminated feed with viruses could move from China to the United States. And that's what I'll review that with you today and show you how we're using that same model now to study if other diseases, foreign animal diseases, could make their way into our country through the same vehicle, as we say. All right? So this is a model. This is not a real boat moving from China to the United States. Scott's not on the boat. This is a model. So this is, everyone, I always got to say that at first because it's kind of scary stuff I'm going to show you. So this is done under controlled conditions in the laboratory at Brookings. And some of these viruses we're going to talk about, like foot and mouth disease virus, hog cholera, we can't work with those, right, at South Dakota State. The lab's not qualified to handle that level of pathogen. So what we're going to use in some cases here are what we call surrogate viruses. And surrogate viruses are substitutes or proxies. They're viruses that are related to the pathogen at hand, but they come from the same viral family, meaning they're basically built the same way, but they're not the real McCoy. And I'll show you exactly what I mean by that. So we're going to be as safe as we possibly can when doing this study. Now, the study funded, again, and SHIC is where a lot of the money came from, ASV, also Chemin Industries and Kansas State University. So there's a big team of people working on this. And the goal is pretty simple. Can viruses live across the ocean? And do they need a feed matrix or a feed ingredient to keep them alive? It's a pretty simple study. So the first question is, and this is old news for everybody, but why do we do this kind of work? Why do we even bother with this work? This work's very expensive, it's very tedious, but just look at some of these numbers. These are actual costs or losses where we've had an outbreak of classical swine fever or hog cholera or foot and mouth disease around the world. So the Netherlands, 700,000 pigs slaughtered in 1998, 1999, and another 1.1 million killed as a preemptive slaughter. Foot and mouth disease in the United Kingdom in 2001, 7 million animals were killed. You see the cost in U.S. dollars, $12 to $18 billion across all the industries of agriculture, because that disease, as you know, affects ruminants too. It's not just pigs. There's been some nice publications on the annual cost of FMD in endemic, infected countries or free countries should an outbreak occur. Billions, billions, and billions. And even our experience with PED, it's not a foreign animal disease, it was a transboundary disease, but look what PED did to our country back when it rolled in 2013. 7 million pigs died, which is about 10% of our national pig crop. So we've had experience with it. There's plenty of publications in the literature that said, what if FMD got into the U.S.? What if hog cholera or classical swine fever or even African swine fever? What if these diseases actually came into our country? What would it do to the swine industry, the bovine industry, the grain industry, the tourism industry? And you can see there's all sorts of scary numbers up there from many distinguished colleagues that have tried to put an economic impact on what these diseases cost. Everything's got a B next to it. Billions, right? Not even a million anymore. We're talking billions. So this is scary stuff. This is why we have to do this work. Next question I always get is, well, how does this whole thing start? How does a grain get contaminated? How do raw materials potentially contact viruses in other countries? And if you Google soybean drying in China, you'll have a picture like this come up on your screen. And we've seen this with our work in China and other countries, not just China, but this is how grain are handled in certain countries around the world. It's basically put out on the road after it's pulled out of the field. Cars and people drive over it, it cracks it up, they sweep away the chaff, and they collect the grain. And they prepare it for movement, right? So this is real, I've seen it. Gordon Spronk from our group, who leads our Chinese initiative, has taken me to these exact places where this has happened. So I know this is real. So we know we got big numbers to deal with should it happen, and I think we have a big risk on how it could get started, how the raw materials could potentially get contaminated. All right. So the PED work we've done and published, it really can summarize it very quickly. And I'll show you how we did it, but the take-home message on PED was, of the 14 ingredients we spiked or inoculated with PED virus and put it through a model moving from China to the U.S. that I'll describe for you in a moment, 5 ingredients supported that virus throughout our simulated journey. 2 types of soybean meal, lysine, choline, and vitamin D. Okay? So we showed, and we proved experimentally, that this virus could survive a simulated journey from Beijing to Shanghai to San Francisco to Des Moines over a 37-day transport period, which is how long it actually takes for stuff to move in that route. Interesting enough that we also looked at mitigants. Were there chemicals, were there products out there that could neutralize the virus? And we learned that 2, one which is already on the market by Chemin, which is approved, called Salcurb, it's approved for salmonella control in pigs and poultry, was very effective against killing PED virus, as was what we call the medium-chain fatty acid blend from Kansas State University. So all along with understanding risk, we want to try to understand what are some potential solutions. What can we do about this? Because it's one thing to identify the problem. We have to try to come up with some type of solution. Okay. So that's a little background on the PED work. I'll share the model with you as we get into the foreign animal disease work, but before we go on, I hit it pretty fast. Any questions on the the PED work. We talked about it last year, so I don't want to bore you and go over it in too much detail unless you really want to know some of the ins and outs. Okay? All right. Now, let's go into the current project, and let me explain how we do this. And you can see that instead of PED, we're going to basically do the experiment over again. But we're going to use our surrogate viruses and sometimes even the actual pathogen and try to see if in certain feed ingredients would viruses live across the ocean. Our hypothesis was, kind of based on what we learned from PED, if you got the right ingredient and if you got the right virus, bad things can happen. So it depends on the virus, probably its physical-chemical characteristics most likely, as well as the ingredient. That's our hypothesis. All right, so working with Paul Sundberg, again, from the Swine Health Information Center, we selected 10 diseases from what he calls the Swine Disease Matrix Project. And the purpose of the matrix is to organize diseases in priority of concern to our industry. So FMD is at the top of the list. Obviously, that's got a cattle component to it as well. That's always the top on everybody's lists. But as a surrogate for FMD, we're going to use Seneca Valley virus. You might know a little bit about Seneca Valley virus. It's basically the same size as FMD, 25 to 30 nanometers. It's non-enveloped. It's single-stranded RNA. So the viruses are built the same. Okay? And Seneca causes vessels, as you know, on pigs. So they're very, very closely related. But we can work with Seneca Valley virus in a controlled laboratory setting, and we've got really nice diagnostic tests to look for it, whether it's dead or alive. For hog cholera, number 2, or classical swine fever, we're going to use a cattle virus, bovine virus diarrhea, if there's any people in the audience that worked with cattle over their career. BVD is what's called a pestivirus. So hog cholera and BVD are very similar, related again. Same size, same shape. It's an envelope virus, so all the things I won't bore you with. But we put together a very, very strict checklist to be sure that the surrogate we picked was as close to the actual pathogen as we could. Pseudorabies virus. We've cleaned up pseudorabies in the United States, but it's alive and well in China. And there's some highly virulent strains of it moving around. And so if we can't work with pseudorabies here, but we can work with BVD. I'm sorry, bovine herpes virus 1. So a herpes virus of cattle. We're going to use that as our surrogate to try to simulate our pseudorabies. Vesicular exanthema virus of pigs. That's another vesicular disease. We selected a feline virus, a Cochleacy virus. Again, same family. Good diagnostics. For Nipah virus, we selected dog virus, canine distemper. Both are what's called paramyxoviruses. Swine vesicular disease, we're going to pick an enterovirus. And then the remaining viruses on the list, we're going to actually use the pathogen itself. We're not going to use a surrogate. So we're going to use vesicular stomatitis virus itself. Okay, that's the other vesicular disease of pigs. Circo, we can work with Circo. PRRS, we're going to use the 174 strain as a high-path PRRS model for the Chinese strain of PRRS, which is quite high pathogenic. And we actually are organizing a plan to use the actual African swine fever virus. So we will be working with some surrogates, as you can see in parentheses, but also some of the real McCoys. So I think this is going to add credibility to the study. All right, any questions on the selection process or the thought process behind it, why we have to do this? Pretty common sense. Okay. Now let's talk about the study design. This is the same match we used with the PED. First thing, we're going to try to make this like a CSI investigation. So CSI Pipestone, right? So we're going to try to simulate as close as we can a shipment of products from point A to point B, and I'll go over that. First, we're going to start with the actual ingredients that come from China to the United States. What do we bring into the country from China? Let's use the same ingredients. So we went to a public website called the U.S. Government Harmonized Tariff Schedule, which records the introduction of all products into the United States from any country in the world, whichever port they come in, what the quantity is, the season of the year, et cetera, et cetera, et cetera. So you can go to this website, and I worked with a friend of mine named Dr. Gil Patterson. Gil was at the University of Minnesota at the time, and he was very familiar with this. And I said, hey, Gil, show me what comes from China to the U.S. in, say, 2012, 2013, 2014. Let's start there, and I'll show you what he told me. So we're going to use actual ingredients. And then we're going to take a standardized amount of ingredient and virus and mix it together. And we're going to put it in what's called an environmental chamber. That's that silver thing. That's like a big incubator with a computer on top. And the computer actually changes temperature and relative humidity based on how you program it. This is going to be our boat. This is going to be the boat, so to speak, that starts in China and makes its way to the U.S. Now, we are going to take historical temperature data and historical relative humidity data that actually occurred from Beijing to Shanghai to across the Pacific to San Francisco to Des Moines. We're going to program it into that computer, and every so often during each day of the project, it's going to cycle. Try to simulate again what happens in the real world. I'll show you some specifics on that in a minute. It's going to take 37 days to do all this. That's exactly the time it takes to move product from Beijing to Des Moines. I'll explain in a moment where we got that from. And then along the way, we're going to sample. We're going to set up the ingredients and viruses in quadruplicate, and we're going to sample 4 different times. Sample day 1 post-inoculation. So we're going to, day 0, we spike the ingredients. We put them in the environmental chamber. A day later, we take the first batch out that represents contamination in Beijing. We test them by PCR, virus isolation, and potentially swine bioassay to see if there's live pathogen there. We're looking for, is the virus alive? Then the journey goes on, and about 7 days later, it's ready to export to the United States. It's been in the Anqin terminal at Shanghai. It's sat there for enough time, and the product's ready to move across the ocean. We're going to sample at that point again. Now, it's going to be a different batch, because remember, we set this up in quadruplicate. And we do that because it has power, and it also prevents us from opening and reclosing the containers and potentially contaminating things. Then we're going to let the journey go on, 17 days more across the ocean, which is the time it takes to cross the Pacific Ocean, to the port of San Francisco. We're going to sample at that point. And then finally, we're going to let it go through customs for 7 days, truck up I-80, get into Des Moines. That whole period of time is 37 days. And that's going to be our final batch. So we're going to have multiple replicates of this sampling process throughout each part of the journey. Okay, that's how we're going to do this. Here's what we learned in regards to what comes into the United States from China. So here we've got ingredients that Gil Patterson sent me the names of the ingredients that we bring into our country from China. There's 2012, 2013, 2014. In pounds, you can see how much of each of these ingredients have come into our country, just to the specific port of San Francisco. Okay, this isn't all around the United States, all the ports. A lot of this stuff comes in a lot of different places, but we're focusing on the entry point of this study in San Francisco. So you look at soy oil cake. Okay, that's the material left over after the beans are extruded. Okay, so you've got some junk left over. That comes in. DDGs, pet food, moist and dry pet food. A lot of pet food comes in from China. Soybean meal, believe it or not, we bring in soybean meal from China. That was a mind bender. So was pork sausage casings. How does tissue come in from an FMD positive country? Well, we send bladders, intestines, and stomachs to China, and they process them into casings, and it comes back. That's how that happens, believe it or not. That's a mind bender, too. Lysine, choline, vitamin D. And so that, over those 3 years, is what comes into San Francisco. And again, we're not picking on China here. We're just using that as a starting point, because that's where we think the original PED virus came from. And the Chinese scientists will tell us that. You probably got PED from China. So this could be country A to country B. It doesn't have to, it just starts with China and ends with the United States. Again, I'm not pointing fingers at Chinese people. All right, so that's kind of how we set the stage for what do we bring in? What do we bring in? Now, here's the journey. If you go to a program called crates.com and say, I want to start in Beijing and end in Des Moines, it'll give you the route. Now, I started in Beijing for obvious reasons, for all the manufacturing of agricultural products that occurs there. But not too far from Beijing is called the Anhui province, and that's where the PED variant that is 99.8% similar to the U.S. variant was recovered. So that's why I started there. I started in the eastern part of the state, or country, sorry. So day 1 post-inoculation, we're going to take a set of samples. Day 8 post-inoculation, we're now down in the Anqing terminal, Shanghai. Day 25 post-inoculation, we've crossed the ocean. Day 37, we've cleared customs and we've trucked that product up I-80, and we are now in Des Moines. So that's how we come up with the sampling points, and that's how we come with 37 days. The temperature data and relative humidity data came from historic websites like Weather Underground. So this shows you the 37 days of the study on the x-axis, the period of time that we were trying to simulate. So late December, early 2013, since PED showed up in 2013 in the United States in April, we thought, let's take some weather data prior to that period of time just as a starting point. We went to the weather sites and we found what happened temperature-wise, what happened relative humidity-wise on land and sea. And so I made this graph for you to show you kind of the variability in relative humidity and temperature and the stability over sea and the variability over land. So these data are plugged into the computer and they rotate 4 times a day for temperature, 3 times a day for relative humidity. So we get some variation into our model, not just a straight refrigerator temperature. The real world doesn't have a straight refrigerator temperature. It's got variation every day. And what was really interesting to me was the stability over sea. And that's this part. Can't see that too good with the pointer, but that's this part here. And I actually found some data from a Xerox company paper, where they put data loggers in their containers across the Pacific Ocean during this period of time to understand what the potential effects were on their papers, on their inks, on their cartridges. So I was able to take actual data from the container itself as it was moving across the ocean exactly at the point I wanted to help put this timetable together. So just dumb luck. But it's interesting to me how stable things were over the ocean. Note as well, 40 degrees Fahrenheit up to maybe 50 degrees Fahrenheit was our range of temperature. How many people think viruses like that kind of weather pattern? Yeah, you're right. Viruses don't like that kind of weather pattern when it's that. That's pretty warm for a virus. Viruses typically like winter days, okay? How about that relative humidity? Look how high and low that relative humidity went over land. That's not very virus-friendly either. So these are conditions that are not favorable for a virus to survive over a long period of time. It'd much more like to be in the freezer. Okay? All right, but these are the real data. All right, I'll wrap up. Thoughts at this time, and they're preliminary, but I think they're starting to see some interesting trends. Surrogate viruses representing FAD pathogens demonstrating varying degrees of survivability by ingredient type during a simulated journey across the ocean. Soy products might have something going on here. Survival could also be influenced by the virus structure itself, as we've been just discussing, and the fact that the virus is in the container by itself, it can't live throughout the journey. There needs to be some type of protection to that virus. What we're doing right now are the viruses right there listed in phase 2. We're not through the process yet, but we've started the Nipah virus, PRRS, and vesicular stomatitis. These are enveloped viruses, and they appear to be quite labile or not very stable outside the host. We're not done yet, but they are struggling. These 3 are struggling. Phase 3 is Circo. That's non-enveloped. That will be interesting, as is the enterovirus. And then the African swine fever is a very, very stable virus that can live in meat. It can live in very low and high pHs and live in the soil for extended periods of time and high temps. And so my guess is these remaining 3 viruses will be very stable, will probably survive quite a bit, in contrast to the ones we're working on right now. And then again, we're going to try to look at some mitigation at the end of this and see what are some products that could neutralize these viruses along the way. So a lot of work left to be done, but I wanted to give you some insight on what we're learning at this time. And I think there's three things, last slide here for you, the impact, I believe, of this work. It's a first objective data that shows that contaminated feed ingredients could potentially serve as vehicles for viral movement around the world. It's a laboratory model. It's got all sorts of limitations on size, et cetera, but it is showing some interesting data on survival. The outcomes I'd like to see come out of the project are three. Raise the awareness. All of you should know today, after you leave the room, that feed ingredients may be risk factors for virus movement. Number two, identify what are the high-risk combinations. What are the ingredients that support the most viruses? Perhaps it's soy. Let's see if that's repeatable. Because if we know the high-risk combinations, we can then start to focus our efforts on the highest risk ingredients. And then let's look at some mitigation strategies. How can we neutralize that virus? Because in the end, for this study to be really valuable for our country, as well as Canada and our continent in general, we must affect significant change in the North American decision-making process in regards to the feed industry. I'm looking at mandatory treatment of high-risk ingredients. If we can identify an effective treatment, and we can identify a high-risk ingredient, let's just say if you're going to bring it into this country, you've got to treat it with this. And get marked and validated, and we know it's safe. Why can't we do that? Number two, maybe we just need to make better ingredient sourcing decisions. Make them on health rather than price. Don't buy some of this stuff from countries with FMD. It's not that, crazy of a thought. So that's going to take discussion. It's going to take a lot of give and take. But these are the first set of data that actually says this is a new box here. This is a brand new room. This is a place we've never been before. And when you look at it in this perspective, it kind of makes sense.